everybody. I hope everyone's having a wonderful day. So we're going to get started with the next topic. It's part of an introduction. It will be algorithms. So I've so far talked about what data structures are, talked about what a problem is, that problems have input sizes. So remember, you can think of the input size as the number of items for which you encode your input in, where each one of the numbers, like say if I give you an array, you can think of each one of the numbers as some encoding of a fixed number of bits that your computer would be able to read. Okay? We're going to keep it kind of simple like that. So what we're going to do is I'm going to kind of put everything together. So I have to give us a working definition of an algorithm. Now there's several different algorithm definitions you might encounter. Some are more formal than others. This one will do mostly fine in an undergraduate level computer science class. There is a more formal definition, but that's beyond the scope of this course. But this one is pretty much a working definition that most algorithms researchers use. So it's a pretty good definition. So an algorithm, I'm going to read it with you because this definition is very important. It is an unambiguous step-by-step procedure that takes an input instance of a given problem as input and produces output for the problem instance. So you'll notice that our definition here is tied intimately around problems. So you're going to imagine it like I have some problem, I pluck off one of those problem instances, I feed its inputs to the inputs of my algorithm, and then the algorithm solves that problem. Then we ask the question of if it's correct or not, right? I produce some output, and we say that the output of an algorithm is called correct if it is the solution to the problem instance. So in our example with the sorting problem, remember I gave you some array with some numbers in it, and I want to ask, hey look, if I have a bunch of numbers, the solution is that sorted in non-decreasing order from smallest to largest. So you got to look at this as if I gave you an algorithm and it correctly outputted that sorted order, then we say the output is correct, okay? So I want to give you a picture. I like drawing this picture for students because I find it really helps put everything together that we've been talking about. So I find this is a pretty helpful picture. Because there's a lot of terminology kicking around. I just really want to cut down to the middle of everything. So imagine I give you a problem instance. So remember, this is one of those dots in my circle where the circle represents all of my instances. And each one, remember, is some input, and that input is encoded with some number of bits. And that number of bits, that's our input size, okay? So usually we refer to the problem instance as inputs, specifically as the input instance or as inputs. In fact, you'll find very often that people will use this phrase and that phrase synonymously with the word instance, like I said the other day. So an input instance, like I said, has input, which I'll just refer to as input instance, and it has a solution. Likewise, I have this other definition I just gave you of an algorithm. So I have an algorithm. So I have this notion of an algorithm. The algorithm has inputs. So these would be your parameters that accept inputs. And it has output. So how exactly does this algorithm, what did we say in this definition? We say that it takes an input and produces output. So what does the algorithm do? Well, it takes an input. It will produce some output, right? But to do that, I have to be able to do something, right? I have to give some input instance as input, right? So I give this to the algorithm, and it gets given as input. That input gets processed by the algorithm using this step-by-step procedure to produce output. And then finally, we just do one last thing to determine if it's correct or not. We check if it's we don't know if it's correct or not. We don't know if this is correct. Now, remember, I told you that the problem instance doesn't, it's really just this input. I'm just associating with its solution to make it easier to understand. So, that being said, you can't literally just be given this and the solution as part of the input of the algorithm. It's only the inputs, those parameters that are being assigned values. So we don't necessarily know all the time if our algorithm produces correct output, which I'll get to in a moment. So this is kind of like the picture I want you to have in your head. So I take inputs from the problem instance, I feed it as input to the algorithm processes that, produces output. And then we just simply want to know if this is correct or incorrect. Okay? Now, there's a few things I want to highlight about our definition of an algorithm. The first thing is that it's unambiguous, and that means that if I give you an algorithm, there's no way you can twist, you can mangle what I've said. It has to be precise in such a way that it's exact, meaning that if there isn't going to be some way that you couldn't follow my algorithm and get the wrong answer if indeed my algorithm were correct. Likewise, you want to think of unambiguous in a contextual way, because you might ask, okay, well, how do you know if you're following the person's algorithm correctly? Now, algorithms are often given in various forms. In words, like in English, you'll find very often I do this. You'll find I'll use pseudocode. So this is a machine-independent, programming code that doesn't really have any one solid convention to it. But you'll find that I'll follow a consistent set of rules to write down what it should look like. So it could look like words, but the words have to be unambiguous to the reader. So it means that when I say unambiguous, it has to be clear enough for your audience. So that's what I mean by contextual. So if I'm writing an algorithm up to a bunch of algorithms experts, they won't be very particular or picky about me skipping a couple of steps here or there, because they will be aware of the things I describe. So I might describe a name of an algorithm, they will know what that algorithm is, or I may even just say, solve this problem, and I'll give the name of the problem. They will know what that problem is, and they'll know about algorithms for that problem. However, at the level for which you're introducing an algorithm, you want to avoid doing things like this. You want to be as clear as possible without any ambiguity. Some way that somebody can take what you've written and twist it such that it doesn't make a whole lot of sense to them. So you got to be not overly charitable with your audience. That's basically what I'm saying. Likewise, it is step by step. That means that each operation that you perform, there isn't a way you can split the operations into multiple ones that are occurring all at the exact same time. Every operation has to precede a previously stated operation. It's so-called deterministic. Now, this is in contrast to some other types of processes you may encounter in future studies, say, for example, parallel algorithms. Parallel algorithms, they do operate in a way that I described, sort of, but not entirely, because technically still, each one is being operated on in parallel by different machines. Here, my definition still applies because I'm assuming there's just one computer, okay? We'll talk more about what that means later. So, this is what we're going to consider an algorithm.